Let me first record. Okay, now the recording is running. So now if you want to type your name into the chat, we'll have your record for attendance. And if you hadn't been given the data package already, then we'll make sure that you get reimbursed for your data after today. And we'll also have your attendance records so that we can make sure that you get data for next week also. Okay, so now if you want to write anything in the chat, now you can write your name so that we have your attendance. Okay. And I'll remind everybody periodically to do that if you haven't done so yet. Okay. So welcome everybody. Before we start, I just wanted to ask Aby, is there anything else administrative that you wanted to say? So I think you got muted. Okay, so I want to thank Abraham, who's here, who's helping organize this program behind the scenes, along with Sanjay and Deborah and Charles. So it's and of course Asimana Randolph. Okay, so thank you, welcome everybody here. So let's get started. So many of you were here last week. Several of you were not, but there's not really anything that we did last week that's going to be completely important for this week. So if you want to recall, last time we talked about the basic ideas of calculus, okay? And we talked about certain problems that calculus is trying to solve and certain applications that calculus has in the other sciences, the natural sciences, and the social sciences. And then we also talked about what you need to know in order to do calculus, right? And the most important thing that we mentioned is this idea of function. Function is the most fundamental input to calculus. Okay, and so we're going to have two classes this week and next week where we talk about functions before we really start moving on to calculus. Okay, and so today we're going to talk about functions kind of in the abstract. Just what is a function? What kinds of properties can it have? Things like that. And then next week, we'll talk more about the specific types of functions that we're going to frequently encounter in calculus. So today, abstract functions, next time, the specific functions. Okay, and so before we discuss functions, we're going to discuss something called relations, which is an even more basic concept than functions. And I think I looked over the Liberian math curriculum for secondary school, and both relations and functions are part of the curriculum. So hopefully, even if calculus is more advanced than what's mostly in the curriculum, this material on relations and functions is still going to be useful for everybody. Okay. So that's the plan for today. We'll talk mostly about relations, and then we'll say something about functions. Okay, so before we talk about relations, we have to talk a little bit about sets. Okay, so I have to say what I mean by a product. Okay, so let's say that we have two sets. We're going to call them A and B. Now, a set, remember, can just be anything. So like the real numbers is a set. The integers is a set. The numbers 1, 2, and 3 are sets. You can have a set with, the colors red, blue, and green. So just kind of any collection of anything is a set. So maybe I should just say, maybe let me mark this down over here before I even move on. So just examples of sets, which we write in certain ways. So we could write a set like the numbers 1, 2, and 3 is an example of a set. And we write it with these curly brackets. You could also have a set with, -1, -2, and -3. That's also a set. Or you could have the set of all real numbers. This is often written as R. So this is the real numbers. Or you could have a set of all of the integers. This is usually written as Z. Okay, the integers, remember what the integers is equal to. It's equal to all of the whole numbers that are either positive or negative. Okay, that's called the integers, this set Z. And then there's a whole bunch of other sets that aren't even, numbers at all. As I said, I can make the set whose elements are red, blue, green. Or I can have a set that's, the set of, all countries in the world. Okay, so it doesn't have to be, strictly mathematical, but we use, the name set just means in math a collection of stuff. Okay, and usually our sets are going to be numbers, but not always. Okay, so let's say that we have two sets and we call them A and B. Then we can form a third set between them that's called the Cartesian product of A and B. That's named for Descartes. And what that is it's the set of all ordered pairs where the first entry in the ordered pair is from A and the second entry in the ordered pair is from B. So let me give an example here. So example, let's say that A is this set 1, 2, 3, and B is the set -1, -2, -3. Then if we want to take this Cartesian product A cross B, what is it if we want to list all of the entries? Well, it's all the ordered pairs where the first entry is in 1, 2, 3, and the second entry is in -1, -2, -3. So in this case, it's small enough that I can write the whole thing down. So that's 1 - 1, 1 - 2, 1 - 3, 2 - 1, 2 - 2, and 2 - 3, and 3 - 1, 3 - 2, and 3 - 3. Right, so I just form every single ordered pair, every single possibility where the first element is either 1, 2, and 3, and the second element is either -1, -2, or -3. Okay. And one of the reasons they call it a product is look at the number of elements, right? This set over here has 3 elements, A, and the set B has 3 elements, and the product has 9 elements. It's 3 times 3, right? Because we have 3 choices for the first entry and 3 choices for the second entry. So you can see by putting them in this box that the total number of possible choices is 9. Okay, so this is one example of a Cartesian product. Maybe the other example that's the most important one in calculus is if you take A to be the real numbers and B is also the real numbers, that's fine. A and B can be the same thing. Then A cross B is what? It's the set of ordered pairs of real numbers. And the set of ordered pairs of real numbers, that's just what we call the XY plane, right? So that is A cross B is the XY plane, right? I mean, it's everything. What are the elements of A and B are all numbers A cross B, all ordered pairs A comma B with, it's a set of all A comma B with A a real number and B a real number. Okay, remember this notation here means is an element of. So we have that A is an element of the real numbers and B is an element of the real numbers. Okay, and this is why it's called, if this example tells you why it's called a product, this example tells you why it's called Cartesian, right? Because the XY plane is sometimes called the Cartesian plane. It's from Descartes. And so if you have the set of all ordered, by using this product formulation, you get the XY plane. Okay, so if I have any two sets, I can form their product, which is just a new set that has ordered pairs. First entry is from A, second entry is from B. Okay, so any questions about these examples or about what I'm doing with these sets and Cartesian products?
Russ?
Yes, James?
I got a question. You said when set A is let's say the set of other pair of real numbers, and that was set B, you call it the X and Y plane. That means the value on the X axis and the Y axis in the Cartesian plane, right?
Exactly. Yeah. I mean, really, with my letters here, I could have called it the AB plane if I wanted to, But usually we understand this as the XY plane, where the first coordinate is the X value and the second coordinate is the Y value.
I want to ask a question because on the Cartesian plane, you have both negative and positive numbers can appear on the Cartesian plane, right?
Yep.
So that means negative numbers are also real numbers?
Yes. Yes. So real
Okay.
numbers means the positive and the negative numbers and all the fractions and all the irrational numbers. The entire number line is the real numbers.
Okay. Thank you.
Yeah.
Very clear.
We call real as opposed to imaginary numbers. You don't have things like the square root of -1. But the whole number, the real numbers are just the number line. Okay. Great. Other questions? Okay, so by the way, the R is for real numbers. This Z is for Zahlen, which is the German word for numbers. That's why we use Z for integers over here. Okay. Okay, so this is how we form the Cartesian product, right? We take all of these possible ordered pairs. So now I want to talk about what a relation is. So this is the definition of relation. So let's say that A and B are sets. Then we say that a relation between A and B is just any subset of their Cartesian product. And if A equals B, instead of saying a relation between A and A, we just say a relation on A. So if the Cartesian product is every ordered pair, then a relation is just some of the ordered pairs. Maybe all of them, maybe none of them, maybe some of them, right? It can just be anything. There's no restrictions on what a relation can be. Okay, so, and just as a matter of notation, if we give the relation a name, if we call it R, so if we name this relation R, to say that an ordered pair is in the relation, we can also write it as shorthand. We say ARB. This means that AB is in the relation R. Okay, so this is maybe a little abstract. There's a lot of letters and definitions, so let's just look at the examples and see what we have. So let's look at this example one. Let's say that A is the set 1, 2, 3, and B is the set 3, 4, 5, and then we can have a relation between A and B, which is, what do we need to know for a relation? We need to know which ordered pairs are we taking. So we're going to take the ordered pairs, exactly the ordered pairs where the B coordinate is 1 bigger than the A coordinate. So the B is equal to A plus 1, right? So in this case, A cross B, so this is how you say A cross B or A times B. So that would be the set of every possible ordered pair. So I'll have 1, 3, 1, 4, 1, 5, and 2, 3, 2, 4, and 2, 5, and 3, 3, 3, 4, and 3, 5. But if I want to take R, and so this R, by the way, is not the real numbers R. Notice I'm drawing this just as a regular R. When I draw the real numbers R, there's an extra line over here. This is just a regular R for relation. So the relation says, don't take all of the ordered pairs, right? Only take the ordered pairs where the B coordinate is the A coordinate plus 1. Okay, so I look through all these ordered pairs. Well, 1, 3, that's no good. 1, 4, no good. 1, 5, no good. 2, 3, that's okay, right? Because 3 is 2 plus 1, right? So this is going to have the ordered pair 2, 3. 2, 4 is no good. 2, 5 is no good. 3, 3 is no good. 3, 4, that's good because 4 is 3 plus 1, right? So I'm going to take 3, 4, and then 3, 5 is no good. So the relation is just, it's not all the ordered pairs, it's just these two. It's just 2, 3, and 3, 4. So it's like we're defining a property that you need for it to be the relation. Okay. Question?
Yeah, Andrew.
Yes, Hassan.
Yeah, what you just did, it simply means that no two ordered pairs will have the same first coordinate.
Well, okay, this is talking about functions, but we're not talking about functions yet. Where this is just relations, right? Relations have absolutely no constraints. You can do anything you want with them.
Or you can do anything.
Yeah, so I could have a relation, and we'll see. a relation where we have ordered pairs. We're going to do 5 examples that are going to show all different kinds of relations. Okay. And then functions are a special kind of relation, which exactly has the property that you're saying, that no 2 ordered pairs can have the same first component.
Okay.
That all, bro?
Yeah, question?
Yeah, that all, bro. I
Hello?
got a question.
Yes.
Yeah, that all, bro?
Yes, James?
I'm saying that the relationship is B is it should be greater than A. That is the I1 to A. There's always a case that it has to be greater than A, or sometimes B can be less than A.
No, I'm just making, this is just an example. I could easily make a relation where it only works if B is A minus 1. This is just an example. There's no rules on relations. The only rule is that it's some subset of the ordered pairs. You can make any rule that you want at all, and that's always a relation. Okay? So in this example, B is always going to be bigger than A because B has to equal A plus 1. But you could make a different relation between A and B, where maybe you only take the case where B is equal to A, for instance. In that case, that relation would only have 3, 3 in it. It wouldn't have anything else. But for this relation, B is always going to be bigger than A because we're imposing the rule that B is A plus 1. But that's just this example. That's not the definition of a relation. Just this example. Is that clear? And so for notation here, yes, Princeton?
Yeah, where we have the relation of these 2, 3, and 3, 4,
Mm-hmm.
and we are saying that if you are collecting a relation with B is greater than A, right?
Well, it's not B greater than A. It's B has to equal A plus 1. This is the rule. It has to be exactly 1 bigger than A.
Okay.
Okay. So just, as a matter of notation here, right? So notation here, we would write 2R3, and we could write 3R4. That means that 2 is, you could read it as 2 is related to 3, and 3 is related to 4. And if you take something that's not in the relation, like maybe 1, 3, we would say 1 is not related to 3. So we'd have an R with a cross with a line through it. Okay, 1 is not related to 3. And, for instance here, 3 is also not related to 3. Okay, so these would all be statements. In the order state, yeah, in the general statement, no specific formula. I just gave this as example 1 for, here's a relation that's given by a specific formula. But we're going to see other relations that are given differently. So part of this is just to introduce, like, what are all the different kinds of relations you can see. So this is one basic example.
Yes.
Yes, other questions? James?
Yes.
Yes, James?
I'm seeing far. Far is also related to 3.
No, because by this definition, 3 is related to 5 only if 5 is 3 plus 1, right? But 5 is not 3 plus 1. So 3, 5 doesn't make it into the relation. Only 3, 4 does.
All right.
Okay.
Thank you.
Great.
So
Other questions? Yes.
Yes.
Yes, Princeton.
Yes. So in this case, I'm understand that the first number, if I want to, it will give you the next number, right?
Right.
Yes. So, for example, I think James was just asking a question here concerning the 3, 5. So there's no way I want to 3 to give you 5.
Right.
If you get to 2, 3, you can add 1 to 2 and will give you a 3. If you add 1 to 3, it will give you 4.
Right.
So I think
That's why we've got
that's a
this.
simple understanding. Yes.
Mm-hmm.
Okay.
Yep, that's a simple understanding. Exactly. That's why we get these. We get 2, 3, and we get 3, 4, but nothing else. Okay. Any other questions? Okay, so let's look at a second relation that's going to be very different. Okay, here's a second relation. We can let A be the set of all counties in Liberia. Okay, remember I said sets don't have to be numbers. So I'm going to take the set of all counties in Liberia, and I'm going to let R be the relation on A. Remember what that means. Relation on A means that it's a relation between A and itself. A and A. Okay, so it's a relation between A and A. A relation on A is given by you have ordered pairs A and B if and only if A and B share a border. Okay? So in other words, right, we have that AB is in the relation if A borders B. Okay? And so we're not geography teachers here, so I don't know if everybody knows exactly where everything is offhand, but I included this map if we need a little look to see where everything is. So I want to write out what are all the ordered pairs in this relation, right? And so probably the easiest way to do it is to just go county by county and start with the first go through the list of counties as possible first elements. So we can find what are all of the ordered pairs in this relation that start with Grand Cape Mount. Okay, well, looks like it has borders with two counties, right? With Barpolu and with Bomi, right? So in my relation, I'll have to do some abbreviations because it's going to be a big set. Well, I have Grand Cape Mount and Bomi, and I have Grand Cape Mount and Barpolu. Okay, that's it for Grand Cape Mount, right? So now let's do Barpolu. That borders Grand Cape Mount, Bomi, and Bong, right? So I'm going to probably start abbreviation. So Gbar and Bong, Gbar and Bomi, and Bar and Grand Cape Mount. Okay. So it's going to take a little while to go through, but I think it's worth it because we'll see it. So then let's go Lofa. So Lofa borders Barpolu and Bong. Sorry, yes, question? Yeah. Yes, hello,
Yeah,
George?
Apollo Lofa.
Right.
Apollo Lofa.
Oh, but okay, yes, I'm going one by one. I'm doing first all the ones where Grand Cape Mount is first. Then Barpolu Lofa. You're right. Oh, sorry. Did I miss it? Yes, I missed it. Thank you.
Yeah.
Sorry. Yes. Okay, yes. Okay. Barpolu Lofa. And then we have Lofa, Barpolu, and Lofa, Bong. I think that's what we decided it. Maybe we won't do all of them. We'll go. People here are from Nimba and Montserrato, so mostly, right? So maybe we'll do all the ones with Nimba and all the ones with Montserrato, and then you'll get the idea of the pattern, and I won't draw the rest of them. So Nimba has lots of, it looks like we've got Bong, Grand Bassa, River Ses, Sino, and Grand Gede. So let's draw all those. Let's write all of these. So we have Nimba, Bong. We have Nimba, Grand Gede. We have Nimba, Sino. We have Nimba, I've now forgotten, Nimba, Grand Bassa. And we have Nimba, River Ses. That's all of them, right? Yes. Okay, and then let's just do Montserrato also. So we've got Bomi and Margibi and Bong. Okay, so we also have Montserrato, Bomi, Montserrato and Margibi, and Montserrato and Grand Bassa. No, sorry, Montserrato and Bong. Okay. Okay, and so on. Okay, you can write these all, but we get the idea now, right? So you're going to have this large group of ordered pairs, right? Where every ordered pair consists of two counties, where the first county has a border with the second county, right? And this is a perfectly good relation And as I think Hassan was saying before, right, here you do have two different ordered pairs with the same first element, right? The same first entry, right? You have Grand Cape Mountain Bomi and also Grand Cape Mountain Barpolu, right? So, so this is some very big relation. It probably has like something like 50 elements in it. But you know, it's a relation and it doesn't necessarily satisfy any mathematical properties. And it doesn't have any rule that, you know, you can only have one ordered pair with a given first element. It's just a relation, right? But it will turn out that it satisfies some properties that that we're going to talk about later. And in particular, this is going to be what's called a symmetric relation. So we'll talk about that in a little bit. Okay, but this is another example of a relation. Again, just anytime you have two sets, in this case, the same set, and you want to just choose some of the ordered pairs by using any rule. So in this relation, the rule that you're using is just, I take the ordered pair if the two counties border each other. Okay, so we'll just write etc. here. Okay. Okay. Any questions on this? Okay. All right. Second. Okay. Okay. So this is the second example of a relation. Okay. What's a third example? Okay. This is just our map. Okay. So what's the third example of a relation? So let's say that A is the set of all real numbers. And again, we're going to take a relation on A. So it's ordered pairs of real numbers. And it's given by X is related to Y if Y is equal to X squared. Okay. So we can't write down all the ordered pairs because there's going to be infinitely many here. But we have another way of doing this, which is, well, remember that if A is the real numbers, so recall, if we're looking at the Cartesian product A cross A, which is what we have when we have a relation on A, that A cross A, otherwise known as the real numbers cross the real numbers, is the XY plane. Okay, so that means if I draw the XY plane here, then I can try to represent this relation by just saying, you know, drawing a curve in the XY plane that represents the XY values that satisfy this relation. So what we're saying is that we have something is in the relation, x comma y is in the relation if and only if y equals x squared. This is just another way of saying the points in the relation are exactly the points on the graph of y equals x squared. So what we do here is we graph. Okay, so we graph y equals x squared, which we know looks like a parabola. This is the graph of y equals x squared. Okay. And then in this case, the relation R is represented by the points on the graph of y equals x squared. Okay, so the entire Cartesian product is the whole xy plane. The relation is saying which ordered pairs do we take? We only take the ordered pairs where y is equal to x squared. So, you know, R contains, or maybe I'll write it like this. So we have, for instance, that, you know, 1 is related to 1, and 2 is related to 4, and 3 is related to 9, etc. But, you know, 1 is not related to 8. And in particular, 4 is not related to 2, right? The order matters here, right? So 2 is related to 4 because 4 is equal to 2 squared, but we don't have it in the other direction, right? Because 2 is not equal to 4 squared, okay? So in this case, you know, and in general, when you have a relation on A, where A is the set of real numbers, then you should be able to draw that relation in the plane. You can use a graph, or maybe sometimes it's a region, to represent, you know, what that relation is telling you. Okay. Any questions on this? Okay, it's clear. Okay. Great. Okay, let's move on. A few more examples. So example 4, again, A is the set of real numbers. R is going to be a relation on A, and it's given by X is related to Y if X squared plus Y squared equals 1. Okay? So our situation is the same thing. We're going to graph it again. So I still have my XY plane. I'm going to give a little graph, XY, but now we're trying to graph X squared plus Y squared equals 1. So I want the ordered pairs that satisfy X squared plus Y squared equals 1. So who remembers what kind of shape this is, this graph?
A circle.
I think that's
Yep, that's exactly right. So this is a circle, and it's a circle with radius 1. Okay, so we just get a circle with radius 1. So this is the point 1, 1 over here. This is -1 and -1. Okay, so this graph right here is exactly the graph of X squared plus Y squared equals 1. Okay. Oh, why it was X equals Y squared, Y equals X squared? This is just, no, not X equals Y squared. So Y equals X squared. It's just an example. I'm just going through examples of relations. Okay, so I'm just doing examples. So this example, sorry,
Andrew?
question? Yeah, Hassan?
The student asked that question, why you got X squared. Maybe you can do that example in your tablet.
Right, yeah, so you could do
Maybe.
X equals Y squared also, right?
Yeah,
So we could
tabular.
have that as
Maybe.
example 3.5. Maybe we'll go there. Yeah, so I mean, if we wanted to do X equals Y squared, I'll throw in an extra page here. And if we wanted to have, you know, oh, sorry, what did I just do? Okay, yeah, if we wanted to have, you know, A is equal to the real numbers, and R is given by X is related to Y if X equals Y squared, then you can just draw. Again, if we have the x-axis here and the y-axis here, we draw x equals y squared. And if you remember, that looks just like the parabola, but it's on its side instead of opening up. Okay, so this here is the graph of x equals y squared. Okay. Okay, so this is what we would have. It's the same idea. And maybe over here, we had x squared plus y squared equals 1. It's also a different graph. It's a circle. And one of the things, if you remember, we'll talk about this later, but this is one of the ways that you see that relations are more general than functions, right? Because this graph of a circle is representing a relation. If you remember about functions, there's something called the vertical line test, and that means that this thing is not the graph of a function, okay? But that's okay. It doesn't have to be the graph of a function. It's still the graph of a relation. And so relations give more general possibilities than functions. Okay. All right. Any questions? And don't worry if you don't know what I'm talking about. I'm going to define function later today. But for now, we're just talking about relations. All right. So any questions about this? Yes, James?
Yeah. Then we grab the circle equation where x squared plus y squared equal to 1. So the value, the -1, +1, and -1 will be added together. Will still be equal to 1.
Yeah, because you know what these really what these points are. This is the point 1, 0, and this is the point 0, 1, and this here is the point -1, 0, and this here is the point 0, -1. So in all of these cases, if we take the x coordinate and square it, and we take the y coordinate and square it, and we add them together, we always get 1, right? So here we get 1 plus 0, 0 plus 1, 1 plus 0, and 0 plus 1. Okay, so all of these points lie on the circle because they satisfy x squared plus y squared equals 1. And then there's a whole bunch of other points on the circle also. So you can have, maybe this point over here is maybe 4/5, 3/5, right? That also satisfies x squared plus y squared equals 1, right? Because this squared would be 16 over 25, and this would be 9 over 25. So adding them together, you get 25 over 25, which is 1. Okay, so there's lots of other points on this circle. And if you were with us when we did the trigonometry last time, any point that's of the form cosine theta, sine theta is on this circle for any angle theta. Okay. Yes, question, James? Yeah.
Yeah, I'm confused of having another point, like you're talking about theta or the cosine rules, like you having 4 over 5 and 3 over 5. Is that satisfies the triangle that defines Stochastic rule?
Yeah, that angle is probably about 37 degrees. It's inverse sine of 4/5,
Okay.
whatever that is. But if you have an angle that's about 37 degrees, then its cosine is about 4 over 5, and its sine is about 3 over 5. So there's some specific angle that's very close to 37 degrees that has its cosine is exactly 4 over 5, and its sine is exactly 3 over 5.
Thank you. Understand that.
You're welcome. But it's not going to be like a nice angle. It's going to be some irrational angle with a lot of stuff after the decimal point. It's not just like 30 degrees or 45 degrees or something like that.
Yeah, Andrew?
All right, again, we'll talk more about trigonometry also next time. For today, we're just more getting the idea of what's a relation, what's a function. So next time, we're going to go over the trigonometric functions. Yes, Hassan?
Yeah, I love how you stick to your objective, because that guy always like to take you higher, 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 higher.
Okay, thank you. Appreciate that.
Okay.
But it's important because we do want to review. We're going to talk about exponentials and logarithmic and trigonometry and all of these things. We need that for calculus also. And that's going to be the main focus next week to review all that. Okay. All right. So for now, this is just another example of a relation, and we can draw it just like everything before. Okay, so we have example 5. This is the last example. So now we take the set of integers. Remember, this is only the whole numbers, but it's still the positive and the negative numbers and 0. But no fractions, nothing irrational, just whole numbers. So we have R again as the relation on A given by x is related to y if x minus y is even. Okay? So what can we say about R? Well, we want to know, when is x minus y even? Well, if we have, so let's look at all the possibilities. Let's say that if xy is equal to, well, let's see, we have 4 choices, right? It could be odd and odd. It could be even and even. It could be even and odd, or it could be odd and even, right? So let's see, if we have an odd number and an odd number, well, is their difference even? Yes, right? Because an odd minus an odd is even. So any ordered pair of integers that's odd comma odd is going to be in the relation. What about even, even? Same thing, right? If I have an even number minus an even number, that's going to be in the relation. So check again. What about even odd? Well, this is no good, right? Because an even number minus an odd number is an odd number. So this doesn't satisfy the criterion of the relation. Okay, so this is no good. We'll give it an X. And also here, if I have an odd and then an even, I take odd minus even, that's going to be odd. And so that does not satisfy the condition of the relation. So that's no good also. So I can say that R consists of all ordered pairs of integers of the form odd, odd, or even, even. Okay, so that's what I can say about this relation, okay? And of course, I can write down a bunch of elements, but it's got infinitely many elements. So this has 1, 1, and 2, 2, and 2, 0, and 3, 7, and 4, -6, and so on. I mean, it's got millions and millions of elements. As long as either both of the entries are odd or both of the entries are even, then everything is fine. This is a little bit harder to graph because A is not the whole real numbers, it's just the integers. But you can try to kind of do a graph where you just highlight. It would be easier if we had graph paper. Actually, maybe I think I do have graph paper. So let me can I do a new page with graph paper? Do I have graph? No. Do I have graph paper? I thought I do have graph paper as an example. No, is there no graph paper? View all templates. Let me just see. Squared paper. There we are. Okay. Okay. So I can do graph paper if I want to try to graph this. Let me again draw my axes, X and Y. I can zoom in a little bit. And then I'm going to draw all the points where both the X and Y coordinate are even. So that's going to look like this. So here's all the evens. Notice I'm skipping 2 spaces every time I move in the X or the Y direction. So this is everything where the X and the Y points are even. I'm only drawing them at the lattices, at the lattice points on the graph. And then I've got to do stuff below the axis also. Sorry, that was a mistake. Here we are. So I'm drawing a bunch of points here where all the coordinates are even. These are all in the relation. And then I also need to do the points where all of the coordinates are odd. Let me erase this. That's a mistake there. Okay. So I also have to do where all the coordinates are odd. So that's going to be like 1, 1, and -1, 1, and -1, -1, and 1, -1. And it turns out if I draw them all, I just get this design where I skip by 2
Hello?
in every direction. Hello, yes.
Yeah, it's Enoch.
Enoch, hi Enoch, welcome.
Yeah, what if you were asked such a question to graph this stuff, and the paper you are using, the analogy you are using, for instance, it doesn't have lines indented like this, or you won't actually be forced to put in those points, right?
Yeah, I mean, you could either just draw the lines yourself, which is not so bad,
Okay.
or you could just try to, put the dots with the correct pattern. In that case, it's probably better to draw the lines yourself.
Okay.
Yeah. Okay, so this is roughly what the relation looks like. And of course, it's not the whole thing. It goes on forever in every direction. But for, just as an example of what this relation looks like, it's not really like a graph of a curve. In this case, it's a pattern of dots in the XY plane. Okay, because we're only looking at integers and we need them either both to be odd or both to be even. Okay. All right. So I'll just go back. That's the picture. I'll go back to this. Okay, so these are our examples of relations, and there's many, many more. But these are going to be some good test cases for the properties that we're going to talk about. So by the way, if for anybody who came in later than we started, remember to please type your name into the chat so that we have your record for attendance, especially people who weren't part of the class last year, so that they don't know how this works. So the way we know attendance so that we can give you data for next week is by you type your name into the chat so that we have a record that you were here. Okay. All right. Any questions on example 5?
Yeah, the Roberts, I got a question on example
Yes,
5.
James.
Yeah, so you're saying that if the value of R of the relationship is X minus Y and it's even, you're saying that X can be odd, Y be odd, and X can be even and Y be even. If you place number 4 minus 4 equals 0.
Right.
So is that even, comma, even? Is always a working odd cases?
Yeah, that's fine, right? 4 minus 4 is 0. So that's just even. So that's fine.
So by saying it's equal to even.
Yeah. 0 is even. Yeah. So to clear up any ambiguity, 0 is always in every context an even number. It is not a question. It is 0 is just as even as 2. Always. The definition of an even number is a number that's 2 times an integer, and 0 is 2 times 0. So it is an even number. Yeah, so 0 is always considered an even number. All right, any other questions? Okay, so let's move on. Okay, so those are examples. So let's talk about properties that a relation can have. Okay, so let's say that we have a special type of relation. It's a relation on A. So it's always going, going from a set to itself. Okay, so then there's kind of there's really 4 important properties that a relation can have, but there's 3 of them that we're going to talk about on this page. So the relation, we call it reflexive if A is related to itself for every A and A. Remember what this means. This is saying that A comma A is always in the relation. Okay? So the relation R is symmetric if whenever A is related to B, you also have that B is related to A. Okay? So this is a fancy way of saying that, but it just means that if you have AB, then you also have BA. A relation with that property is called symmetric. Okay? And then transitive is the most complicated one. It's saying that if you have AB and you have BC, then you also have AC, right? So in other words, this is saying if AB is in R and BC is in R, then AC is in R. And if you have all 3 of these properties, then, sorry, that should be and. Then if you have all 3 of these properties, then you're what's called an equivalence relation. Okay. So if a relation is both reflexive and symmetric and transitive, then it's what's called an equivalence relation. And you think of equivalence relations as being kind of saying that 2 things are going to be related if they share some property in common. That's usually what an equivalence relation means. So what we're going to do is, again, when you first see a definition, it's not always so clear. But we're going to go back to all of our examples, not example 1, because that wasn't a relation on a set. That was a relation between 2 different sets. But for examples 2, 3, 4, and 5, that were all relations on a set A, we're going to go back to them and we're going to check all of these properties. Check to see, are they reflexive? Are they symmetric? And are they transitive? Okay, these are kind of the 3 most important properties of a relation other than being a function, which is the last property we'll talk about. Okay, so we're going to go check all of the properties of the example. So I'm going to build a little table. Okay, so this is going to be the example. So we have examples 2, 3, 4, and 5. And we're going to check. I'll just go all the way to the end of the page. So we're going to check if it's reflexive, if it's symmetric, and if it's transitive. Okay, and so we're just going to answer this for all of these. Okay, so let's go back over the definitions. Remember that reflexive means that for everything in your set, the ordered pair with both entries identical is in the relation. Symmetric means that if you have AB, then you also have BA. And transitive means that if you have AB and you have BC, then you also have AC. Okay? So let's go back to our examples. So we'll start with example 2. So this was the example with the counties. So we want to know, is this relation reflexive? Do I have all the ordered pairs where the first entry is a county and the second entry is the same county? Well, by the way, we define this really no, right? I mean, we're only having the 2 counties that share a border between them. I mean, I guess you could say my wording here is a little ambiguous. So should I have Lofa here, right? Does Lofa share a border with Lofa? It's a matter of language interpretation, but I think the way that we were talking about this, we interpreted this as no. they don't share a border. It's only two counties sharing a border if they're next to each other. So in this case, we don't have Lofa Lofa, and we don't have Nimba Nimba, and we don't have Montserrato Montserrato, right? So that means this relation is not reflexive, okay? Because we don't have the ordered pairs that is a county and then the same county again. So I'll even write this back in red. This is going to be not reflexive. What about symmetric? Well, if two counties A and B share a border, then do B and A also share a border? Well, the answer there is yes, right? I mean, two countries sharing a border, that is a symmetric relation. If A borders B, then B borders A, right? So for instance, here we have, Grand Cape Mount and Barpolu, and we also have Barpolu and Grand Cape Mount, right? So anytime you have an ordered pair, you also have the reverse, because two counties sharing a border is a symmetric relation, okay? If I have A and B share a border, then B and A also share a border. So this is symmetric. Okay. And now what about transitive? So if A borders B and B borders C, does that mean that A necessarily borders C? Maybe we should look at the map to see this, right? So for instance, Lofa borders Bong, and Bong borders Nimba, but Lofa does not border Nimba, right? Just because one county shares a border with a second county, and that second county shares a border with the third county, that doesn't mean that the first county shares a border with the third county. This is what transitive means. Transitive would mean that if Lofa bordered Bong and Bong bordered Nimba, then Lofa would also have to border Nimba. But that's not true. And so what that means is that this relation is not transitive, okay? A borders B and B borders C, that does not mean that A borders C, okay? So this here is not transitive. Okay, so it is symmetric, but it's not transitive. Okay, so if we go back to our table over here, we're going to have, is it reflexive? No. Is it symmetric? Yes. And is it transitive? No. Questions about this example here?
Yeah.
Yes.
Yeah. Please
Yes,
let's
George.
go back to the map.
Mm-hmm.
Yeah, please let's go back to the map.
Yep.
Yeah, in a case of Bapulu, Cape Mount, and Bomi.
Mm-hmm.
Yeah, so is that transitive?
Right. So that would be evidence for transitivity, right? Because Grand Cape Mount borders Barpolu, and Barpolu also borders Bomi, and Grand Cape Mount borders Bomi. So that would be evidence that it is transitive. But we're talking about whether the entire relation is transitive. So it's a very good point. And the entire relation is transitive only if this always works. Okay?
Okay.
So only if this always works. So if you can find even one example where it doesn't work, that means the relation is not transitive. So your example is an example that does work, but there's also examples that don't work. And transitive is only if every example works.
All right.
Okay. Great. Other questions? So let's do example 3 and go back to more math. So same questions. Is it reflexive? Is it transitive? Is it symmetric? Well, so is it reflexive? Do we have that every point of the form x comma x is still there where the x and y coordinates are the same? Well, no, right? This is going to be not reflexive, right? Because for instance, 2 comma 2 is not on the graph. Right? 2 comma 2 is not on the graph, right? So, and again, just like symmetric and transitive, for the property to hold for the relation, it has to hold for every possible example. So sure, 1 comma 1 is on the graph. That would make it look like it's reflexive, but 2 comma 2 is not on the graph. So I found even one example here where 2 comma 2 doesn't work. Then where 2 comma 2 doesn't work, then that means that the relation is not reflexive. Okay. So this is not reflexive. Is it I'm going to do a couple of these examples, and then I'll leave the last one for you guys to do. So is it symmetric? Well, no, right? Because I have 2 is related to 4, but 4 is not related to 2, right? So in this case, the order matters, okay? So this is going to be not transitive. And if I wanted to justify that, I would say that 2 comma 4 is on graph, but 4 comma 2 is not. Can you not hear the audio? I think that's probably on your end. I think I'm coming through. Okay. Make sure that your volume is turned on. Okay. And then lastly, is it symmetric? That's a little bit harder to see, but the answer is going to be also no. It's not going to be, oh, sorry, this should have said not symmetric. Not symmetric. And it's also going to be not transitive. For instance, 2, 4 is on the graph, and then 4, 16 is on the graph, but 2, 16 is not. Okay. I have 2, 4 and I have 4, 16, but I don't have 2, 16. Okay, because 4 is 2 squared and 16 is 4 squared, but 16 is not 2 squared. Okay, so this is not reflexive, not symmetric, not transitive. And for each of these to show that it's not, you just need one counterexample. So I have one counterexample for reflexive, one counterexample for symmetric, and one counterexample for transitive. That's enough. So when we fill out the chart is going to say no, no, no. Okay. Just want to remember how much time we have left. I want to see if I want to skip any of these. Yeah, you know what? Let's skip number 4. We'll do number 5, but I'm just going to skip number 4. So I'm going to leave this as an exercise for you to do. You can do number 4 with the circle. So we're going to leave that as an exercise. And what about 5? So 5 is a little interesting. So 5, remember, was this relation on the integers where an ordered pair was in the relation if and only if the difference was even. So question, is it reflexive? If I have a number and itself, is that always going to be in the relation for this case? Yes, right? So Robert says yes, exactly, right? Because I have everything that's of the form odd, odd, or even, even, right? So if I have a number and itself, well, either the number is odd, so I'm going to have odd, odd, or the number is even, and I have even, even, right? So it definitely is reflexive. Okay. What about symmetric? So what I'm really asking is, if x minus y is even, is y minus x also even? This is a math question. General, I have 2 integers. If x minus y is even, do I know that y minus x is also even? Yes, that's correct, right? So I have, it's true, right? Because x minus y and y minus x are negatives of each other, right? So that means if one is even, the other's even. So it will be symmetric. Or alternatively, we know that we have all the ordered pairs. If you're in R, you're either of the form odd, odd, or even, even. So if we switch your 2 coordinates and you started out odd, odd, you're still going to be odd, odd, right? 2, 0, or sorry, 3, 7 is odd, odd. 7, 3 is also odd, odd. Or if you started out even, even, you're also going to be even, even. So 2, 0 is even, even. and 0, 2 is also even, even. So in this case, this relation is symmetric. And then lastly, is it transitive? It's a little bit harder. Maybe I'll leave it as an exercise, but in fact, this is going to be transitive. Okay, so that's telling me that if x, I mean, maybe it's not that hard. I mean, we should say it, right? So let's say that x and y are in the relation. So if, let's say first that x and y are both odd. So if x is related to y and y is related to z, well, if x is related to y, then x and y are either both odd or both even. If y is related to z, then y and z are either both odd or both even. And so if both of those are true, the only way that can happen is if x, y, and z are all odd, or if x, y, and z are all even. And in either of those cases, x will still be related to z, right? Because if x is odd, z is going to be odd. And if x is even, then z is going to be even. Okay? So this is transitive, right? If x and y, the word we use in math is parity. Parity tells you whether it means whether a number is odd or whether it's even. So if x and y have the same parity and y and z also have the same parity, you can conclude that x and z have the same parity. They're either both odd or they're both even. So this is going to be transitive. Okay. So we've got, in this case, this is going to be yes, reflexive, yes, symmetric, and yes, transitive. And what that means in this case is that it's what we call an equivalence relation. So number 5 is an equivalence relation. Turns out that number 4 will not be an equivalence relation. So 5 is the only one that has this. Okay. Okay. All right. Any questions there, James?
Yeah. I find it difficult to understand the transitive, let's say the transitive relationship, because I still don't really getting it clear. That's why I please try to talk.
So should we understand it in the context of example 5 here? Do you want to go over it in the context of example 5?
Yeah, that'll be okay.
Okay, let me write something down, because I didn't write anything, so I only talked there. So let me write something. So let's just see. So example 5. Let's say, why is it transitive? Well, suppose that xy and yz are both in the relation. Okay? We want to show that xz is in the relation. Okay? This is what we want to show. If x, y, and yz are both there, we want to show that xz is there also. Well, there's 2 possibilities. Well, and the first possibility would be that x is odd. Well, if x is odd, well, xy is in the relation. And we know that if x and y are in the relation, they either both need to be odd or both need to be even. So if x is odd, that means that y has to be odd. This is odd. So this means y is odd. And then yz is in the relation and y is odd. So if y is odd, then you need z to be odd also. Okay, right? We use xy being in the relation to know that y is odd, and then yz being in the relation tells you that z is odd. And so is xz in the relation? Yes, because x is odd and z is odd. And we know everything of the form odd, odd is in the relation, right? So xz is in the relation. Second possibility, exactly the same, but everything is even. So exactly the same reasoning. The second possibility is that x is even. And for the same reason, this means that y is even. And so z is even. So xz is in the relation. Okay. So in both cases, xz is in the relation, right? And then this maybe gives you the intuition for why we use this word transitive. It's kind of the status of x being odd. It, transfers its status to y, which in turn transfers the status to z. And so that it's transitive because it means the status of being odd has been transferred from x all the way over to z. Okay. So if x is odd, that means y is odd. If y is odd, that means z is odd. That means x and z are both odd, and it'll be in the relation. Or if x happens to be even, exactly the same thing. X even means y has to be even. Y even means z has to be even. And so that means x and z are both even. So only possibility is x and z are both odd, or x and z are both even. Either case, they're in the relation.
So, that over.
Yeah.
I think I'm getting it clear. So that means y minus z should be equal to even number if both are all are even, right?
Yes.
Okay,
So, right, we could do this with the original definition also. You could say that if x minus, or another way of seeing it, right? Here's another way of seeing it. Or if you have that x minus y is even and y minus z is even, then what's x minus z? Well, then x minus z is the same thing as x minus y plus y minus z, right? Because the y's cancel each other out. And this is equal to even plus even, which is equal to even. So this is another way of seeing it where you don't need to break things into two possibilities. The relation said we're in it if the difference is even. So if xy is in the relation, that means x minus y is even. If yz is in the relation, then y minus z is even. So we want to know, is x minus z even? Well, it is, because you can write x minus z as x minus y plus y minus z. And so by our assumption, that's an even number plus another even number, which means in the end, we have to get another even number. So that's another way you can see it. So by the way, Benson, I think it's probably on your end because I think the audio is clear. So I don't think there's anything I can do about the audio. You may want to try to log out and log back in and see if that helps. Okay. Okay. All right. Any further questions on this? Okay, so let's move on. Okay, so now let's talk about functions. Why are we doing all this relation stuff? Because eventually the point is we want to talk about functions. Okay, so a function is a very special type of relation. So now we're going to let R be a relation between A and B. So we're no longer requiring it to be a relation on A, right? We can have one set A for the first coordinates and another set B for the second coordinates. And so now, and I think Hassan said this earlier on, we say that R is a function from A to B if for each A and A, there is exactly one B and B with AB being in R. Okay? So, so a function from A to B means that for every element in A, there's exactly one ordered pair in the relation. Okay? And if a relation is a function, we usually use a slightly different notation. We write, f as a function from A to B. And we write, if A, B is in the relation, we use this notation. We write that f of A is equal to B. And this is what we have as a function. And in calculus, when we're looking at functions, we often have that A and B are both going to be the real numbers. So again, kind of a lot to digest, but let me just give an example here. let's do our first example, but I'm going to change it up a little bit. So let's say that A is the real numbers and B is the real numbers. And my relation is given by, A comma B is in the relation if B is equal to A plus 1. Okay. Maybe actually, just to make it simpler, let's not make it the real numbers. Let's make it the integers. Okay. Okay, so what are my elements of R? Well, R is going to have all ordered pairs of integers where the second coordinate is 1 plus the first coordinate. So I'm going to have things like 0, 1, 1, 2, 2, 3, 3, 4, etc. And then I'll also have negatives. So I'll have like -1, comma 0, -2, comma -1, -3, comma -2, and so on. Okay, and so let's observe for every integer A, there is exactly, for every integer little a, there is exactly one A comma B in the relation. Right? If A is equal to 0, the only ordered pair that starts with 0 is 0, comma 1. If A is equal to 3, the only ordered pair in the relation is 3, comma 4. If A is equal to -2, the only ordered pair in the relation is -2, comma -1. Okay? So this is what it means to be a function. It means that if you know the first coordinate, then you automatically know the second coordinate. There's only one possible choice. And not only that, but there is a possible choice. Okay, so if this relation were missing 0, comma 1, then it wouldn't be a function anymore, or at least it wouldn't be a function from A to B. Okay, it would have to be a function with a smaller set. Okay. So a function means it's exactly what Hassan was talking about. You can't have two different ordered pairs with the same first coordinate. Okay, and you also can't be missing a first coordinate in your ordered pairs. You have to have them all show up exactly once. Okay. So what we're going to do is go back through all of our relations again and, check whether they're functions or not. Okay. But before we do this, are there questions about the definition? By the way, I should say in this case, we would write, f of 0 is equal to 1, and f of 1 is equal to 2, f of 2 is equal to 3, and so on, right? This is just the relation way of presenting the standard function f of x equals x plus 1, right? So we say f of whatever the first entry is in the ordered pair gives you the second entry. And it's well defined because you know there's only one possible choice for the second entry. Questions?
Yeah, good day, sir.
Yes, Prince.
Remember?
Yep. Hi,
Yeah,
Prince.
okay.
Yep.
Yeah. So, with a relation hour, with a relation hour, is it only going to be defined by 0, comma 1, 1, comma 2? Would there be any other numbers to start with the exception of 0, comma 1?
Oh, I mean,
because
the order that you
where
write
the 0 is equal to 1.
Yeah, well, so I mean, you don't have to write these. I just wrote these in order for exposition, but the order of elements in a set doesn't matter. So I could have started with 3, comma 4 and then 4, comma 5. It doesn't matter where I start. The point is that R has every ordered pair in it whenever the second entry is one more than the first one. And they're both integers.
Oh, okay.
Yeah. So I just wrote them in this order just
Okay.
for ease of presentation.
All right, thank you.
Okay, you're welcome. Other questions? Yeah, Theophilus? Theophilus, I see you have a hand raised. Okay, well, we can't hear you. Okay, let's go through the examples. I think with the examples, you know, what's a function and what's not will be clear. So we're going to check which of our relations are functions, right? So in this case, we have relation, and we're going to say, is it a function? So we had relation 1, 2, 3, 4, and 5. Okay, so we got to go all the way back to relation 1 now. Do here. Okay, so go all the way back to relation 1. Back here. Okay, here we are. Example 1. Okay, so we had AB is in our relation if and only if B is equal to A plus 1. So our relation has only the ordered pairs 2, 3, and 3, 4. So it looks good, right? Because we don't have multiple ordered pairs with the same first entry. We just have one ordered pair that starts with a 2 and another ordered pair that starts with a 3, right? But the problem is we don't have any ordered pairs that start with the 1, right? So this relation here is not a function from A to B, because if you basically the function is not well defined at 1. Okay? So this function is not, this relation is not a function from A to B. Even though it doesn't have any repeats, it's missing an element that has a 1 as its first coordinate. And the point is, if you tried to define this as a function, okay, you'd have f of 2 equals 3 and f of 3 equals 4. But what would f of 1 be? You don't know, because it's not in there. And that's why this does not work as a function. Okay, so this example 1 is not a function. So I'm going to say here, not a function. At least it's not a function from A to B. Okay, you could say that it's a function if instead of 1, 2, 3, if you just had 2, 3, then you could say that this relation is a function from that set to B. But it's not a function on the entire set A, because no ordered pair starts with 1. Right? This is going to be not a function from A to B. Theophilus, anytime you want to talk, just call out. I see you have a hand raised, but I don't know if you can talk. Okay, so that's not a function. What about here, our Liberia example? Well, certainly not going to be a function, right? Because, for instance, if I have Lofa, there's lots of different ordered pairs that start with Lofa, or maybe not lots, maybe only 2, right? But Lofa borders Barpolu and also Bong, right? So this is not going to be a function because I have 2 different ordered pairs with the same first entry. I have Lofa Barpolu and Lofa Bong. Okay, so this is going to be not a function. Okay. Right, as long as you can find, again, you want to show that something's not true, you just need one counterexample. So I found one county that borders at least 2 other counties. That means this bordering relation is not a function, okay? Because we have more than one ordered pair starting with Lofa. Okay, and in fact, I think with more or less every county, we're going to have more than one ordered pair. Yeah, I think every county borders at least 2 other counties. So this, in fact, will fail to be a function with every possible first coordinate. Right, every possible county will have more than one that it borders. Okay. Okay, so this is not a function. Any questions on this? Yes, James.
Like the first example, I talk about 1, 2, 1, 3, it's not being a function, like in this example. So because it's not a function, is it because you don't have any number you can add to A that will be consistent to all of the other pairs?
Right. I mean, so it doesn't work because if you wanted to start with 1, then the next entry would have to be 2. You'd have to have 1, 2. But 1, 2 is not in the relation because I define the set A and B that B doesn't have 2 in it. So 1 comma 2 is not even in the product. So it's certainly not in the relation. So the way I define my A and B, I don't have anything in my relation that starts with a 1. If instead I had taken B to be like 2, 3, 4, 5, then I would have 1 comma 2, and then this would be a function. So if I change B from 3, 4, 5 to 2, 3, 4, 5, then my relation would change from 2, 3, and 3, 4. It would become 1, 2, 2, 3, and 3, 4. And in that case, I would have a function. But in this case, I don't have enough ordered pairs to make it a function. Whereas in example 2, I have too many ordered pairs to make it a function.
Thank you.
Does that answer the question?
Yeah,
Hello.
yeah, thank you.
Hello.
Hello.
Good. Yes, hello, George.
sir.
Yeah.
Yeah, even by looking at the product A plus B,
Mm-hmm.
the option there, the products there, it
Mhm.
also signify that it is not a function because you have the repetition of 1 as a domain, 1 of 3, 1 of 4, 1 of 5. So
Mhm.
it is repeating there. So the first entry is repeating, so it cannot be a function.
Exactly. So if I took a different relation that was just the entire set of ordered pairs, if my relation was just A is always related to B, no matter what, then my relation would just be this entire set of all these ordered pairs, and then that would not be a function, exactly because we have multiple ordered pairs that start with a 1, right? So the entire Cartesian product here is also not a function. It is a relation. You could take the relation. That's everything. That's fine. But in this case, it would not be a function. Great. Other questions? Okay, so this is not a function. This is not a function. What about example 3? We want to know, basically, look at all the ordered pairs. For every x, is there exactly one y that corresponds to that x? Well, we are given y equals x squared, right? So if I look at all of the ordered pairs, everything along this graph, what we see is that for every x value, maybe I'll put an x value over here, there's exactly one y value that's on the graph, right? So what I'm gonna do is draw what I call a vertical line. This is an example of what's called the vertical line test here. And what I see here is that every x value has exactly one corresponding y value. Sorry that the writing is so small. So every x value here has exactly one corresponding y value. And that means that this is a function, right? If I look at my ordered pairs, there's going to be exactly 1 for any given x value, which is I draw this vertical line and see where it hits the graph. It's always going to hit the graph in one place. And so that means that it is going to be a function. Okay. So in this case, every x value has exactly one corresponding y value. It is a function, and the function is given by, what is f of x? It's x squared. So this is kind of the bridge from relations in this abstract sense to functions in the way that we usually talk about them in calculus, right? So a function is, you have all these ordered pairs like 1, 1, and 2, 4, and 3, 9. And so what we say is that f of 1 equals 1, and f of 2 equals 4, and f of 3 equals 9, and so on, right? For every x value, we have exactly one y value. Questions? What about example 4? Sorry, was there a question? Yeah, sorry, it's Prince. It's not coming in so clear.
Hello,
Yes.
hello, sir.
Yes, hello. Hi, Prince.
Hello,
Yep, I'm getting you.
French. Yeah.
Hi. Yep.
Yeah, you getting me?
I'm getting you. Yes.
My question was due to the diagram, the graph, to the graph. Yeah,
Right.
please, let's get it.
This graph here?
Okay. Yeah, the graph. Yeah, this graph is going upward. Why cause the graph to curve upward?
Oh, I mean, this is just how the function y equals x squared works, right? As x gets bigger, the y, you're squaring it, so it gets even big. It keeps getting bigger and bigger, right? And then remember, even when x goes in the negative direction, the square of a negative number is still a positive number. So as x gets to be a larger and larger negative number, the y, if x is -2, y is 4. And if x is -3, y is 9. And if x is -4, y is going to be 16. And as x gets more and more negative, y is going to keep getting bigger and bigger. So that's why even as x gets very positive, or if x gets very negative, in either case, the y value goes up. And so that's why we have this graph curving upward.
All right.
Okay. Great.
It's understood. Thank you.
Okay, you're welcome. Okay, let's move on to example 4. So now we have this relation, remember, given by x squared plus y squared equals 1. Is this going to be a function? Well, no, right? Because I've already even drawn 2 ordered pairs in this relation, 0, 1 and 0, -1, that are both in the relation. And they both have the same first coordinate. They both start with a 0, but in this one, the second entry is 1. And in this one, the second entry is -1, right? So this is going to be not a function, since 0, 1 and 0, -1 are both in the relation. Okay. And another way you can see that is if I look at x equals 0 over here and I draw the vertical line, well, this vertical line hits the graph in 2 different points. Okay, this vertical line hits the graph in 2 different points. So sorry, as the thank you, Robert. Yeah, that's exactly right. As some people have low battery, hopefully you'll be able to look at the recording. Thank you. We only have another 10-15 minutes, so we'll finish soon. All right. So this vertical line is going to hit the graph in 2 points, and that doesn't work, right? So it's not a function, and we can see it graphically because we have 2 points on the graph that are on the same vertical line. Okay. Okay, and this is against the rules of functions. And so lastly, we have this example 5, and then again, we also see that it is not a function. For instance, I have 2, 2 and 2, 0. So this is also not going to be a function, right? Because we have 2 different ordered pairs that both start with a 2. Okay, and 2 different ordered pairs that both start with a 2. So this is not going to be a function. Okay, and you can even see it with the picture. Kind of this picture also fails the vertical line test, right? If I draw the vertical line at x equals 2, doesn't look like a normal graph, but if you go through x equals 2, this here represents the point 2, 0, and this represents the point 2, 2, right? They both lie on the graph. Okay. So let me just fill out the chart just for completeness. I'm trying to remember what we said. I think what we had was that only number 3 was a function. So 3 was yes, 1 was no, 2 was no, 4 was no, and 5 was no. This isn't anything new. This is just what we've done by looking through, I'll just say C slides with original relations. Okay. All right. So the last thing I want to say is just, okay, yes. So let me, right. So what did I want to say? The vertical line test. Right. Okay. So just to recall and be very clear, when we have a function that we can graph, something like this, or if we have a relation that we can graph something like this, then we can see whether it's a function or not by doing what's called the vertical line test. And the vertical line test means every vertical line that I draw should hit the graph in exactly 1 point. That's what's going to make it a function. Okay, so every vertical line should hit the graph in exactly 1 point. So if it hits it in 2 points, it's no good. And if it hits it in 0 points, this circle also has no ordered pairs that start with 2. That's too far out, right? So if I start with 2 and I draw this vertical line, then that's not going to hit the circle at all. That's going to be a problem too. Okay. All right. So, okay. So that's what a function is. And in calculus, we're mostly dealing with functions. Okay. So let me just mention some quick properties of functions. So we're almost done. So let's say that we have a function from A to B. Then the set A we call, so a function from A to B just means, what does this mean? Maybe I should say, so this is just a relation between A and B that is a function. That's what I mean there, right? So the set A is called the domain, and the set B is sometimes called the codomain or the target space. You'll see either of those words. The domain and the codomain. Okay. And now the function is called one-to-one if we don't have any two different elements in A that map to the same, I guess I should say the same element of B. Okay. And if A is B and they're both R, then we can see this graphically using what's called the horizontal line test. So let me show this example. Let's maybe do the same example that we had before. So let's say that we have our function now is the one that's given by the graph of y equals x squared. So this is y equals x squared. This passed the vertical line test. But let me look at the horizontal line test. So let's say I draw a horizontal line maybe at height 2. So I'm going to draw this horizontal line. And what we see is that this horizontal line hits the graph at 2 different points. Oh, maybe I don't want to do it at height 2. Sorry, let me say at height 4. Well, this here is the point 2, 4. And on the other side, I have minus 2, 4. So what we have here is 2 different ordered pairs with the same second entry. Okay. When I draw a horizontal line, if it hits the graph in 2 places, I'm getting 2 different ordered pairs with the same second entry. And when that happens, we say that this fails the horizontal line test. Maybe I'll state on the next page exactly what I mean by the horizontal line test, but what I mean is that passing the horizontal line test should mean that every horizontal line hits your graph at most once. It's okay if it doesn't hit the graph at all, but it can't hit it twice. Or another way of saying that is that you can't have 2 different ordered pairs with the same second entry. Okay? If you have 2 different ordered pairs with the same second entry, then your function is not what's called a one-to-one function. Okay?
Yeah, so Andrew?
Yeah, Hassan? Yep.
Yeah, the vertical line test, we can say, is the opposite of the horizontal.
I wouldn't call it the opposite. I would call it complementary. So the vertical line test is to test to just see if you are a function at all. And then if you are a function, the horizontal line test is to check to see if you're a one-to-one function. It's a special kind of function. So I'd call them complementary, not opposite. And they're not the same.
Yeah, they are not the same. Very different.
They're not the same, but that doesn't mean that they're opposite, right? They can both be true or they can both be false, or one can be true and the other's false. So I call them more that they test for different things. Yeah. So the horizontal line test tests for whether a function is one-to-one,
Yeah,
The vertical line test tests for
yeah,
whether it's a
yes, sir.
function.
That all right?
Yes, Prince?
Yeah, that all right?
Yeah.
Yeah, so can we say this right? It's a function.
Yes. So this is a function. We already saw
You
this.
getting?
Yeah. So this is a function. We already saw this. This is example 3, right? This is just example 3.
I said, can we say the graph? Yeah, can we say the graph is a function?
When you say the graph is the graph of a function. Yeah, so it's the graph of a function. That's how I would say it. Okay. So this relation, which is given by this graph,
Okay,
is a
okay,
function. Yeah. So say this, so I'll just say this is a function, but not one-to-one. Okay. So maybe let me state this all, and this will be the last thing I say, and then we'll finish. So let me state this all and just give a more or example. So, in summary, suppose we have a relation on R and we draw its graph. And we draw its graph. So 1, if every vertical line passes through the graph exactly once. So if every vertical line meets the graph once, then the relation passes the vertical line test. And it is a function. Yes, of course. So based on the coordinates, there can be different shapes and sizes of the graph. Absolutely. To answer, I think, Harrison's question. So the second summary point is if we graph a function, and every horizontal line meets the graph, and now I'm not going to say once, I'm going to say every horizontal line meets the graph at most once. It's okay if some horizontal lines don't meet the graph at all. Every horizontal line meets the graph at most once, then the function passes the vertical line test. Sorry, passes the horizontal line test. And is a one-to-one function. Okay, so this is the summary, right? So the vertical line test is, does every vertical line meet the graph once? That means you have a function. It means you have exactly one ordered pair with any given first coordinate. And the second one is, once you have a function, you draw the horizontal lines, and do they all meet the graph at most once? And if that's the case, you have what's called a one-to-one function. Okay, so maybe the last thing that I'll do is just draw one example of a one-to-one function. So an example, let's say that I have the relation given by y equals x plus 1. I'm just going to assume that we're talking about the real numbers. So if I draw this graph, this is x and this is y. So y equals x plus 1 is going to be a line. Okay, this is what the line looks like. And notice that every vertical line that I can draw passes through the graph exactly once. And every horizontal line I draw also passes through the graph exactly once. Okay, so this gives not just a function, but it's a one-to-one function. Okay. right? Because it passes the vertical line test. You see any line I draw is going to hit this graph exactly once, and it passes the horizontal line test. Any horizontal line I draw is going to hit the graph exactly once. Okay, I see a question. Is it wise to say that the horizontal line test fails if the horizontal line passes through more than one points? That's correct. That would mean that when the horizontal line test fails, it means you don't have a one-to-one function. As Robert says, it exactly means that you have a many-to-one function. It means you have lots of different inputs that can give you the same output. Or in the language of relation, lots of different first coordinates that can give you the same second coordinate in the relation. Okay. All right, so I think that's enough for today. There's a few homework exercises. I'll send these notes to the chat so you can see them, and of course I'll post the recording on YouTube later today. So for each of these, the homework exercises is I'm giving you 3 different relations, and for each of them I want you to check all of the properties. So is it reflexive, symmetric, transitive? Is it a function? And if it is a function, can you determine whether or not it's a one-to-one function? Okay, so these are the homework exercises. I'm not going to go through them in detail now, but you can look at them in the PDF when I send it over later today. Okay, so the problems will be here. And thank you again for your attention. And so next time, we're going to actually talk about what are the functions that we're reviewing. So we're going to talk about polynomial functions, rational functions, trigonometric functions, exponential functions, and logarithmic functions. So these are the types of functions that we're going to have to review in order to do calculus. Okay. Any questions? A reminder once again that if you haven't yet posted your name in the chat, please write it in so that we can have a record for your attendance.
Another thing here. Hello?
Oh, hi, Sange. Yes.
Yeah, I want to say welcome to all in class 4, year 4 of the online training program. And we have just started the new section, and we have a lot of new people coming in, which will be taking some actions. And if you miss class, we say more, we try to other days and accommodate others. But many people are registering in the chat room, registering to be part of the program. So we want you to please take it serious, and this time we're not compromise. Today, people who are asking me, I send people who entered last year where they want actually send data with a refund data. So if for any reason you come in class and I give you data, you don't come in class, I will not give you data until you start data. So that's what I wanted to say. Thank you.
Thank you. And thank you for organizing, as always.
Hello.
Hello, AB.
Yeah. Okay, let's go to Manima math teachers. Tomorrow we're going to be having a meeting. We still want to have people that are going to be taking part into the class. So by 10 o'clock tomorrow, everybody be there. And we're going to also discuss about the past semester, how to get our certificate. So thank you for attending the class today. And we hope that you continue coming to class.
Thank you.
Yeah, hello.
Hello, yes.
Yes,
Yeah, I want to talk about the meeting, but we don't know the venue. Where exactly we'll meet it tomorrow?
We'll be doing the Faith Academy by 10 o'clock in the morning.
Then please.
Yeah, hello?
Hello?
Yeah.
All right.
Yeah, Dada Abbas?
Yep.
Yeah, thank you so much, Spoons. Thank you so much for the such knowledge that you are just giving us for the past years. I just want to know, maybe if I'm not been aware, for the past class where we have, not class, but this one semester, certificate, I don't know if I have it here or whatsoever, because saying that We haven't got any information from our mother.
No.
Because when it comes, she always calling us. Oh, I don't really know what is it.
So
Oh.
the certificates, we're still waiting to see who is going to sign the certificates from the Liberian ministry. So I need to print them with a space for the correct signatory. I will sign the certificates, and then somebody in Liberia is going to sign them too. And I have to wait to print them until I can write the person's name, and I know who's going to be signing them from the ministry. So that's the delay, because I don't know who's going to be signing them yet in Liberia.
Oh, okay. Thank you so much.
I'm sorry, but they will be there. Don't worry. I have the records. I'm printing them all out. We will send them. I know exactly who's getting certificates. I have that all together. The only delay is I need to know who will sign them in Liberia.
Oh, okay.
Andrew, hello.
Hello.
To that certificate, I met the minister, and the minister was
Sorry, one second. I'm still on.
Yeah.
Sorry.
He said you're going to meet Sanjay, and they're going to either come in America to see whether they can sign it. But I looked at, you're going to send it here. I'm going to stay BB and Sanjay to really talk to the minister to see who's going to sign it.
Mm-hmm.
Because stay behind the minister yet, who's going to sign it? Because you know that new administration now. So there we're having problem there.
Mm-hmm. Okay. Okay, sounds good. All right.
Hello?
Any other questions? Yeah, James?
Yes.
Yes.
I have noticed that majority of the people that they are adding to the group chat are not math teacher. So if you are adding anybody, let them be math teacher. Math or science.
Okay. Yeah, no, I mean, we're going to be, this material is probably most interesting for math teachers or maybe closely related physics or chemistry teachers. So, you know, it's going to be in that direction. That's who it's going to be the most useful for. Okay. All right. Other questions? Okay. All right. So thank you. Thank you so much for attending. And I'm looking forward to seeing you next week. Later on today, I'll send out the notes and I'll post the video. All right. So have an excellent weekend. And I look forward to seeing you next Friday.